A student is provided with a 0.03 mole sample of an alcohol and decides to identify the alcohol using an experiment to determine its enthalpy of combustion. Figure 2 shows the apparatus used. The student finds that when all the alcohol is burned, remembering that that was 0.0300 moles, the temperature increases from 18.9 to 78.1. So let's work out what that change is. That's 59.2 degrees C change. Calculate the enthalpy of combustion. Well, to do that, we need to find the heat energy taken in by the water by doing Q. Heat energy is the mass of the water times the specific heat capacity of water, which they've given us here, times the temperature change. Now, the specific heat capacity, 4.18, is in joules per gram, and our mass of water is not in grams. So let's turn it into grams. 0.25 kilograms is 250 grams. 4.18 joules per gram per Kelvin. So our temperature change is 59.2 on the degree C scale. You need to be careful here. There's a temptation to add to get it onto the Kelvin scale, but the difference is still going to be 59.2. If you did 18.9, add 273, you get 291.9. And if you did 78.1, add 273, you get 351.1. The difference is the same. So you can calculate Q. $61,864 joules. But we've been asked to calculate enthalpy change, which is enthalpy is kilojoules per mole. So we're going to take our 61,864 joules and turn it into kilojoules and divide by the number of moles that we burnt. And we're going to get 2,062 kilojoules per mole. Now, because the temperature rose, our enthalpy of combustion is negative, minus 2,062 kilojoules per mole of fuel. Table 2 shows the enthalpies of combustions of some alcohols. Explain how your answer suggests the alcohol is butan 1-ol. So we're looking at the number, and our number is actually closer to propan 1-ols, but it's bigger than propan 1-ols in size. It's more negative. Why is it not as big as butan 1-ols, and yet it tells us it's butan 1-ol? So the value that you're going to get from this experiment is going to not be as accurate as it could be because of heat loss to the surroundings. And that heat loss is accounting for energy that isn't making it into the water. And so the value that you would expect in a data book is always going to be more negative than the value that you got from the experiment. So we need to write down that something to do with heat loss to the surroundings. So the value in the experiment is less accurate due to heat loss to the surroundings. And then we need to explain that this heat loss means less energy transferred to the water. So delta H will be less, and it's an exothermic number, it's a negative number, so it will be less in magnitude, less exothermic than the data book value. The equation for complete combustion of gaseous pentan 1-ol is shown. Table 3 shows some bond enthalpy data. Calculate a value for the mean CC bond. I'm going to add it to the table and call it X in pentan 1-ol. We need to draw out the structure so that we can count all the bonds. I'm going to do a diagram with just like sticks to represent these CH bonds. So here's my pentan 1-ol with the 5 Cs and all those hydrogens. And then we've got 7.5 moles of OO double bonds, and then we've got 5 moles of CO2 and 6 moles of H2O. And delta H is the sum of the bonds broken on the left hand side minus the sum of the bonds formed in the products. And our answer for the delta H is given here, minus 3388. So minus 3388 equals, what have we broken? So let's tick them off as we go. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11, so big bracket, 11 times 412 plus 1, 2, 3, 4 CC, so 4 of our unknown, plus a CO 360 plus an OH 463 plus 7.5 times 496, big bracket around that, minus, what have we got on this side? We've got 1, 2, but times by 5, so 10 times 805, and 6 times 2 is 12 times OH 463. So let's add up those two brackets. Minus 3388 equals, so on a calculator, 11 times 412 plus 360 plus 463 plus 7.5 times 496. So we've got 9075 plus 4x minus, let's add up the other bracket, 10 lots of 805 and 12 lots of 463, 13,606. So minus 3388 minus 9075, because it's going to the other side, changing sign, plus 13,606 equals 4x. So 4x equals, so we're going minus 3388 minus 9075 plus 13606. 4x is 1143. X equals, divide by 4, 285.75. I'm going to round the 3 significant figures. The other numbers were given up here to 3 significant figures, whole numbers, so 286. The energy stored in fuels can be compared using energy density values measured in kilojoules, so kilojoules per decimeter cubed, so kilojoules divided by decimeters cubed. Calculate the energy density of butan 1-ol. The enthalpy of combustion of butan 1-ol is minus 2,600, so minus 2,676. So the minus means released, kilojoules released per mole, and then we've got the density is 0.810 kilograms per decimeter cubed, and the MR is 74 grams per mole. So we've got to use these units to calculate this answer. So how would we find out how much butanol we've got in? For example, the easiest thing might be to say 1 decimeter cubed, because we want to find out how many kilojoules per decimeter cubed we've got. So let's say if V equals 1 decimeter cubed, then the mass would be 0.810 kilograms. But if we want to use the MR, we need to turn that into grams, so 810 grams. So the moles of butan 1-ol in 1 decimeter cubed equals 810 over 74, which would be 10.95 moles. And we've got 2,676 kilojoules released per mole, and we've got 10.95 moles in a decimeter cubed. So how many kilojoules released equals 10.95 times 2,676. So that's 29,291 kilojoules released in 1 decimeter cubed. So that is our answer. Do we need to give it to an appropriate significant figures? It doesn't actually ask us to give it to an appropriate significant figures, but if we were to round up to 3, we get 23900 kilojoules released per decimeter cubed. And this is not equations that we would normally use, we're just having to use the maths and the units to help us.